Now we will learn about a small sample t-test for our average. So what happens if we have small samples? We just learned about a z-test for our average, but we had to have big samples. Well, what happens if we have a small sample? Statisticians have noticed that there are three main problems when we have a small sample, and we usually say a small sample is anything less than 30. The first problem is that the standard deviation of the sample will be too small. So when we have a small sample, the SC of the sample is usually smaller than the SC of the population. So how do our statisticians fix that? They came up with something called SD+. At least our textbook calls it SD+. And this is equal to the square root of, we'll do our sample size divided by our sample size minus 1 times the SD that we got on our sample. So if you take the SD in your sample and times it by this little correction, it makes it just a little bit bigger, and then it will be a better estimate of our population standard deviation. Our second problem is that our sample isn't big enough to use the central limit theorem. So we know that the histogram of all the possible averages will look normal if we have a large sample. But if we have a small sample, that's just not guaranteed. Okay? So if we have a small sample size, we have to have the data look at least almost normal to do our hypothesis test. It still works pretty well as long as it's almost normal. It doesn't have to be exactly normal, but it does need to be at least almost normal. And third problem, if the sample size isn't big enough, then the normal curve isn't going to be the best fit. So what we'll do is we compensate by using a t-curve instead of the normal curve. This is because a t-curve has more area in the tails. So we haven't seen the t-curve yet. Let's look at it. The t-curve is very similar to our standard normal curve, very similar, but it has one extra property called degrees of freedom. So there's a different curve for each degree of freedom. So I have here, actually let's go to the website first. So on this applet, you can see the blue curve is the normal curve. The red curve is our t-curve. Right now, this is a t-curve with 1 degree freedom. You can see how there's so much more area in the tails with that red curve. So it's not quite as high in the middle because there's a lot more area in the tails, which makes sense when we have small samples. But as my degrees of freedom change, if I change this to like say 9 degrees of freedom, notice how the t-curve got closer to the normal curve. And if I move it over a little bit more to like 11, notice it's getting even closer. And at 13 is closer. And as I move this, I get closer and closer and closer and closer to the normal z-curve. Until about 30, you can't really tell difference. At 50, these curves look almost exactly alike. So again, for really small sample sizes, a small degree of freedom, like 1 degree of freedom, there's a lot more area in the tails, which works better for these small samples. It allows for more variability. But as our degrees of freedom get bigger, notice as they get bigger that those two curves become closer and closer together. So back on our notes, you have it here for your notes later. The dashed curve was the normal curve. You can see a t distribution with 1 degree of freedom. You can see what it looks like with 10 degrees of freedom, and you can see at the 30 degrees of freedom, they look almost exactly the same. Also, you might want to note that the t-curve is symmetric. So that means the area in the left tail will be the same as the area in the right tail, and it's always centered at t equals 0. So we're going to use the t-table to find some areas. Let's first look at the t-table. So here's my t-table. You can see the t-curve, and you'll see I have my little t-value, and it looks like the probability is actually shaded to the right, which is kind of weird. The normal curve is actually the only one that's shaded to the left. I'm not quite sure why they did that, but that's what all the textbooks do. But this one, once we switch to the t-curve, it actually shades to the right. So when we look at this, they also did something different because they have every curve is going to have different percentages for your degrees of freedom, and they couldn't figure out how to do that. They switched the way the whole table is set up, which is why I have notes for you here. So degrees of freedom is down here along the left. The probabilities or chances are up on the top, and inside the table is where you actually have your t-values. Again, that's completely different from the standard normal curve that we've been working with, our z-tables. Now you'll notice your degrees of freedom go down the left side, and they actually go quite a bit higher than 30. You'll notice I start skipping some numbers, and this shouldn't really come up in our class, but if you ever needed a degree of freedom that wasn't on this table, you could just round down. Let's try it out. Let's find the area to the right of 1.81. So here's t equals 1.81, and I want to find the area to the right, and I have 10 degrees of freedom. So I come to my table, I have 10 degrees of freedom. So I'm going to be somewhere in this row, and I'm looking for a t value of 1.81. So t values are in the middle, so here's t equals 1.81. And at t equals 1.81, 10 degrees of freedom, my probability is 5%. Well, what if we have the same thing of t equals 1.81, but I want to find the area to the left? Well, just like when we use the z table, and we had to remember that everything adds up to 100%, we'll do that here. So when I look up 10 degrees of freedom, 1.81, that's the area to the right. So we will have to subtract. So if this is 5%, this will have to be 100% minus 5%. Which gives me 95%. So 95% is my answer here. What if I make it a little bit harder here and I say t is equal to negative 1.81? And you want to find the area to the left. Well, when you look at the table, you might have noticed that there are no negative t values. Well, how are you going to do it? Well, remember that we said it is symmetric, which means the area to the left of negative 1.81 will be the same as the area to the right of positive 8.1. So see how these two areas seem like they would be the same? So area to the right of 1.81 is the same as the area to the left of negative 1.81. So this would have to be 5%. What if I have t equals 0.72 and t equals 1.44, and I want to find the area in the middle, and I have 6 degrees of freedom. So 6 degrees of freedom, and we wanted 0.72, and the area from there to the right is 25%. So from here all the way over is 25%. But I only wanted this section, so I could find the area from 1.44 over and then see what that is first, I guess. So that's 1.44%. Wait, I can't write. Sorry, that's 10%. So the area from here all the way over is 25%, from here over is 10%, so the area in the middle would be, we'd have to subtract. So 25% minus 10% equals 15%. So we're using all of our tricks that we use from our z tables. It's just, now we have to remember that everything is in the right, and there's just a few extra things, but we use all the same tricks. Let's try t equals 3 for 6 degrees of freedom. Okay, 6 degrees of freedom, I'm looking for t equals 3. Notice this is 2.45, this is 3.14. 3 is not actually on the table, so it would be about here. So t is equal to 3 would be right about here, which means that this probability or this chance is going to be somewhere between 2.5% and 1%. Now, I don't really know what it is exactly. I'm not really going to make you guess. We'll just say it's somewhere between those two values. So it is going to be between 1% and 2.5%. We can't really get it any better using the tables. That's okay, we'll just leave it as a range. And finally, what if we want it to the left of t equals negative 2.5? Well, again, we can't look up the left, but we can say, hey, this would be the same as if I drew it out and said, here's t equals 2.5 and looked for the area to the right. So let's go look for 2.5 with 4 degrees of freedom. So it looks like this is 2.13, this is 2.78. So 2.5 being the middle, which means my chance or probability is somewhere between 2.5% and 5%. So between 2.5% and 5%. That would be my final answer. Okay, so for our official small sample t-test for the average, we use this test if we are interested in the population average, we have a small sample size, less than 30, and the data is almost normally distributed. So you should check this, because if you have a small sample size, the central limit theorem can't kick in, and so you do have to have that normal data instead of just relying on a large sample size. Okay, preliminary work. It's going to be about the same as our z-test, but we have to add in a little bit extra. So our observed average is still our sample average. Our expected value for the average is still our population average, assuming that the null is true. But instead of using SD, we have to use this SD plus, so we have to compensate for the fact that our sample size was so small by multiplying our SD by the square root of sample size over sample size minus 1. And the standard error, instead of just doing SD over the square root of the sample size, we'll use that SD plus, since we just found it and we know it will be better. Our test statistic, T, you'll notice we use a T because it's a t-test, but otherwise it's exactly the same. It's still observed average minus expected value of average over standard error of the average. But you'll have something new for a t-test. You'll have what's called degrees of freedom. Remember when we looked at the curves on the T curve? Degrees of freedom affected what it looked like. So you have to find degrees of freedom for your specific curve, for your test. And it will be the sample size minus 1. The p-value we're going to do again just like we did with the z-test. Okay, if our alternative hypothesis is less, we'll shade in the left tail. If our alternative is greater than, we shade in the right tail. And if it's different from, we shade in both tails. 2 remarks. Again, just like before, we don't know for sure what the population average is, but for our calculations, we assume that the null hypothesis is true. As another remark, technically in the real world, the t-test is actually used for any sample size, not just small ones, when you're using the sample standard deviation, a standard deviation that you calculate from your sample. But in our class, if our sample size is bigger than 30 or so, because this is just an introductory class, we can just use the z-test because the final results will be almost identical for sample sizes bigger than 30. And the z-test is just so much easier to do by hand that people have been for a long time just kind of had that tradition that if they have a big sample size of bigger than 30, they know that they'll get almost identical results, so they just use the z-test when they had to do things by hand. Now in practice, in our world, computers do everything, so we just use t-test anytime we have a sample standard deviation. But for our class where we're doing it by hand, we'll just use a z-test if our sample size is bigger than 30. First example, an English exam is taken by 2,000 students. The exam scores are known to follow the normal curve. Now, that's important because when we're dealing with our t-test, we know that our data has to follow the normal curve. So data is normal. Good to know. The teacher says the population average is 75, but one of the students thinks the population average is actually lower. So she takes a simple random sample of 9 students. So my sample size equals 9. She finds that they got these following scores. The sample average is 66.6. And the standard deviation is 18.4. We want to test to see whether the population average really is 75 or if the student is correct. So we're wondering, is the population average less than 75 since the student thinks it's less than 75? So that's our question of interest. So null hypothesis. The null hypothesis is always the boring, equals to, status quo, teacher's right. So this would be that the average of all the students is 75. And any difference in the sample you picked is just due to chance error based on which sample you picked. Now your alternative is what you wanted to show. So is the population average less than 75? So the average of all the students is less than 75. Let's do our preliminary work. Our observed average is equal to your sample average, so that was 66.6. The expected value is your population average if the null is true, so the null says it is 75. Okay, now SD plus, so square root of sample size over sample size minus 1. So sample size is 9, so sample size minus 1 would be 8 times the SD of 18.4. Notice that 18.4 does not go inside the square root. So I get 19.516. Now that we have that, let's find our standard error for the average. So that's equal to your SD plus, so 19.516 divided by square root of your sample size, which is 9. This should give me 6.505. Okay, so again, SD plus, that just helps us a little bit with small samples to get a better result, more accurate result here. Finally, now that we have all of that preliminary work, let's find our t-value. It's going to be equal to your observed average minus the expected value for your average divided by the standard error for averages. So the observed average is 66.6 minus the expected value of 19.516 divided by SE for the average of 6.505. Oh, oops. I looked at the wrong line. The expected value for the average is 75. So 66.6 minus 75 divided by 6.505 equals negative 1.29. See, we need to find degrees of freedom. Degrees of freedom is equal to sample size minus 1. So in our case, 9 minus 1, which equals 8. Now for your p-value. T equals negative 1.29. And our alternative is that we want it to be less, so we will shade to the left. And we have 8 degrees of freedom. Now notice the area to the left will be the same as the area to the right if I did t equals 1.29. So let's go to the table and look up 1.29 with 8 degrees of freedom. 8 degrees of freedom, we're looking for, I just forgot, 1.29? 1.29. So 1.29 would be right about here, between 0.71 and 1.40. So my probability is between 10 and 25%. So between 10% and 25%. Now that is your final answer. You actually just leave it like that. So as far as your p-value, so your p-value is between 10% and 25%. You can't really narrow it down anymore without having a calculator or a computer. Let's see, let's interpret that p-value. It's always more interesting to try and interpret it when it's a range like that. So the p-value always says it's your chance of getting your sample average or something more extreme if the null is true. So we have between a 10% to 25% chance of getting our sample average or something even more extreme if the null hypothesis is true. Now, you'll know sometimes I actually say our sample average of 66.6 if the population average is 75. Sometimes I don't. That's because on the exam, the person might write it with our actual numbers, or she might write it in a more general format. You need to be okay with either one. Okay, our conclusions. Well, 10 to 25% is bigger than our 5% significance level. So big p-values, we will fail to reject the null hypothesis. So it is not statistically significant. And for our actual conclusion, the thing we would tell our boss, we would say, we didn't have enough evidence to say that the true population average is less than 75. So there might be a little bit of evidence, but not enough to really conclude it. We're not really sure, so not enough to say that. Next example, tomatoes of a certain quality are supposed to have an average weight of 5 ounces. I'm a little skeptical. I think the average is somewhat greater than 5 ounces. I select 10 tomatoes at random. Okay, so my sample size equals 10. The average weight of these tomatoes is 5.79, so my sample average equals 5.79. And it has a sample standard deviation of 0.91. So SC equals 0.91. Is there evidence that the average weight of this type of tomato is greater than 5 ounces? So we want to know, is the population average greater than 5 ounces? Or is the difference just due to chance error? What would happen if you use a 1% significance level instead of a 5%? So let's see. First, null hypothesis. Null hypothesis is always like status quo. It's always equals to, nothing interesting. So we would say the population average weight of all the tomatoes is 5 ounces. Any difference would just be due to chance error based on which sample I pick. The alternative is what we want to show, which is the population average of all these tomatoes is greater than 5 ounces. Now, preliminary work. So observed average, that's just equal to your sample average, which will be 5.79. The expected value is equal to your population average. We don't know that, but we're assuming the null is true, so we'll go with the null value of 5. SD plus equals square root of sample size over sample size minus 1. My sample size is 10, so it'll be square root of 10 over 9 times the standard deviation, which is 0.91. So 10 divided by 9, take the square root of that, times 0.91, gives me 0.9592. So just a little bit bigger, just to compensate for that small sample size. And SE average, we'll take that new standard deviation, or our inflated standard deviation, over square root of the sample size, which square root of the sample size is square root of 10. So 0.9592 divided by the square root of 10 gives me 0.3033. Now for your t-value, it's going to be equal to your observed average minus the expected value for your average over the standard error for your average. So observed average is 5.79 minus the expected value, which is 5, over the standard error of 0.3033. So 2.6. So that means basically that we were 2.6 standard errors away from our expected value, which anything over 2 is going to be surprising. So I'm going to guess that that null is probably not correct. I'll probably get a small p-value. Degrees of freedom is always equal to your sample size minus 1, which is going to be 10 minus 1, or 9. P-value, here we have t equals 2.6. We said our alternative is greater than, so I have to shade to the right. And we have 9 degrees of freedom. So 9 degrees we're looking for 2.6. Let's see, that would be right about here. So there's 2.6 between 2.26 and 2.82. That means my chance is between 1% and 2.5%. So between 1% and 2.5%. If I was to interpret that, it would mean that we have a 1% to 2.5% chance of getting a sample average of 5.79 or more if the population average is really 5. So whether you just say like our sample average and leave it more generic, or you say like just a sample average of 5.79, and then you can either say if the null is true, or you can say if the population average is really 5. So on the exam, you might see either way, but it's all multiple choice, so you need to be able to pick out the right one. And for our conclusion, so first, 1% to 2.5% is smaller than 5% significance level. So at 5% significance level, we would reject the null hypothesis and have evidence that the population average is greater than 5. But this problem actually said, notice, what if you use a 1% significance level? So what would happen? What if we wanted to be really, really sure? Now this is just tomato, so it probably doesn't matter, but if you, for some reason, wanted to be really, really sure, but if you wanted to use a 1% significance level, then suddenly a p-value of 1% to 2.5% is bigger than the significance level of 1%. So you would fail to reject the null hypothesis. And for this person that wants to be really, really sure, you wouldn't have enough evidence to say that the population average is greater than 5. So again, different people pick different significance levels based on the situation. If you'd picked 5%, you'd say, oh yeah, I only wanted a 5% significance level, so p-value of 1 to 2.5%, that is smaller. I feel fairly confident in saying the average is greater than 5. But if another person said, I want to be really, really sure, and I'm going to use a 1% significance level, then their p-value is too big, and they would actually fail to reject it and say they don't have enough evidence for them to feel comfortable saying that the population average is greater than 5. So, different significance levels can change your answers. Now, does that change the amount of evidence you actually got? No, so we always report our p-value so people can see how much evidence we got. But it does change your final conclusion of what decision you made based on that specific significance level. Next, a health textbook claims that the average weight of adult males is 72.6 kilograms. You think that the average weight in your town might be different. So you take a simple random sample of 20 men. So sample size equals 20. Their average weight equals 90 kilograms. Oh, I'm going right here. Sample average equals 90 kilograms. And the SC equals 17 kilograms. Let's conduct a hypothesis test to determine if your town's average weight is different or if the difference in your sample is just due to chance error. So the question we want to know is the population let's see, different from 72.6 kilograms. Okay, first step in doing a hypothesis test is to come up with your hypotheses, your null and alternative. Let's do the alternative first for this problem. So we want to show that the population average is different from 72.6. So I would say that the population average is different from 72.6 kilograms. Whereas the null will always be the boring of the population average is 72.6 kilograms. Notice different from, that means when we go to choose which way to shade, we're going to have to shade both directions. This is going to be a two-tailed test, because we're going to have to shade both ways. Okay, preliminary work. Your observed average is just equal to your sample average, so 90 kilograms. Your expected value for your average is what you expected to get, or your population average, which we're assuming the null is true, so 72.6 kilograms. Now SD plus, that's equal to the square root of your sample size over sample size minus 1 times the SD that you got. So square root of my sample size, which is 20, over 20 minus 1, which is 19, times the standard deviation we got of 17, should give me 17.44. So just inflates it a little bit. Now the standard error for your average is normally just SD over square root of sample size. But since we went to the trouble of finding SD plus, let's make sure we use that. So 17.44 over square root of my sample size, which is 20, is 3.89. Now that I've done all that preliminary work, I can find my actual test statistics T. So T is going to be equal to your observed average minus the expected value for your average over the standard error for your average. So our observed average was 90 minus the expected value of 72.6 over the standard error of 17.44. Which gives me 0.997. Sorry, I just looked at the wrong number again. I need to use my standard error, which is 3.89. Try that again. 90 minus 72.6 divided by 3.89 gives me 4.47. So we are 4.47 standard errors away from that value, away from our expected value. That seems like it'd be very surprising. Let's go ahead and find our p-value. This is my 4.47. Oh, this would be 4.47. This would be negative 4.47. I remember how we said it's different from, we have to do both tails, so I will find the area to the right, and I'll find the area to the left. Oh, before I find a p-value though, so I start to look at my p-value and it reminds me, oh wait, I need to find my degrees of freedom. Degrees of freedom is equal to sample size minus 1. So 20 minus 1 equals 19. The thing I like about doing hypothesis tests and statistics is you start with your formula and you're like, okay, I have a formula like T equals this, and you start writing everything and you're like, oh wait, I have to go find the standard error. And so then you remember to do that. Or you look up the p-value and you're like, oh wait, I have to go do my degrees of freedom. So then you remember to go do it. Kind of helps remind you of all the steps. So degrees of freedom, we just said were 19. we're looking for our t-value of t equals 4.47, which is going to be somewhere here off the charts. So somewhere here off the charts. So we would say less than 0.5%. So less than 0.5%. Over here I'd say less than 0.5%. Now because the t-table doesn't go as small as the z-table, we don't usually say almost zero if it's off the chart because it's not necessarily that small. So we'll just stick to less than 0.5%. So my p-value, I need to have both of those tables. So let's add those two areas together. So 0.5% plus 0.5% equals 1%. So I would say we have less than 1% as my final p-value. Let's see. So what are some of our conclusions here? My p-value of less than 1% is smaller than a 5% significance level. So we will reject the null hypothesis, and we can say that our results are statistically significant. And our final thing that we report to our boss is that we are fairly sure, or we have evidence, that the average weight is different from that 72.6 kilograms. Now, we have a little note down here that says, unfortunately, if we do a two-tailed test, all we can say is whether or not the population average is 72.6 kilograms. We can't actually say whether it's higher or lower based on the hypothesis test alone. Now, you could use some logic, you could probably figure it out, but this is back to one of the ethics things again. Ethically, if we only set up our hypotheses to say, is it different then our final conclusion should only say that it is different from, and we shouldn't say higher or lower. So if you really don't know ahead of time, you might want to do a preliminary sample or something, try and figure out what it is, and then do your real hypothesis test with just one tail of saying whether you think it's smaller or bigger. Now let's do a little side note. I've added it to your notes, it's just not on here. So the question is, would your results still be valid if I told you the data was not normal? Well, if you have a small sample size, the data has to be normal. Our sample was only 20, which counts as small. So if the data is not normal, then our results would not be accurate because our sample size isn't big enough to make that central limit theorem kick in. So if the data is not normal, your results aren't accurate. Okay, finally, let's just go through the summary here. So your null hypothesis is always your status quo or default hypothesis. And we have to have strong sample evidence that the null hypothesis is false before we will reject it. When we calculate the test statistic, we assume that the null hypothesis is true. So this is just kind of a bunch of random things that you'll want to make sure you remember. Let's see, the further our actual observed data is from what we expected, like the more standard errors we are away from our expected value, the more evidence we have against the null hypothesis. The p-value is the chance of getting a sample value or a test statistic that's at least as weird or extreme as one we got if the null hypothesis were true. Next, the smaller our p-value, the less likely we are to believe the null hypothesis is plausible. Because if the null was true, we had a very, very small chance of getting what we got. So the smaller the p-value, the less likely we are to believe it. So the smaller the p-value, the more evidence we have against the null hypothesis. That means that the smaller the p-value, more evidence we have for the alternative hypothesis. Now remember, our conclusion is always in terms of that alternative hypothesis, so it's the more evidence we have for what we're trying to show. Okay, a few notes here. The p-value is not the chance that the null hypothesis is true, because some people try and put that, or they might put that the null is false, or the alternative is false, or the alternative is true. They try and make up simple definitions. You cannot make the definition simpler than it is. It has to be what we've been writing. So the p-value is the chance of us seeing our data, our sample average, as far as ways what we saw, if the null hypothesis were true. So if the p-value is small, we tend to believe the null is false. So let's see, we will reject the null hypothesis if the p-value is small. If it is less than 5%, we will say it is statistically significant. If it's less than 1%, we might say that it is highly statistically significant. We'll just add that one word to emphasize that it's just a little bit smaller. And you want to write your conclusion in terms of the real world context of the problem. And the conclusion is always in terms of the alternative hypothesis. So we'd say, like, we reject the null hypothesis and conclude that blah, blah, blah. Or we would say we fail to reject the null hypothesis and conclude that blah, 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 insert terms, whatever your alternative hypothesis is there. Just a few more notes here. So when our data is too far from the predictions of what we think it should be for our theory, that's going to be bad for the theory. People start to disbelieve your theory. So in statistics, our null hypothesis is rejected when the observed value is too many standard errors away from the expected value. Like more than 2 is probably going to be bad for it, right? Now, lack of significance, having a big p-value, remember, a big p-value means that we will fail to reject our null. Having that big p-value does not imply that the null hypothesis is true. Just because we don't reject it doesn't mean we're saying it's true. It just means we didn't find any evidence against it, or we didn't find, instead of maybe any, you might want to say enough evidence against it to reject it. A significant result, a small p-value, when you reject the null, does not mean that we have proved the alternative hypothesis is true. All that means is we just have evidence for the alternative. Remember, in statistics, there are always chances. Even a small chance is still possible. So we don't ever like to say that we've proved it. We just have evidence for it. And due to convention or tradition, if our evidence isn't strong enough to convince us to reject the null hypothesis, we don't say we accept the null. Instead, we say we fail to reject the null hypothesis, or we don't have enough evidence to reject the null hypothesis. And final thing to remember here, statistical significance, which means we are sure statistically, which happens when you have a small p-value. So small p-value means we found lots of evidence, we're fairly sure statistically speaking. That does not mean practical significance. Practical significance means, is it a big enough difference to actually matter to anyone in the real world? Because sometimes you might have a difference of only like 0.1 and you might be really sure that it's a true difference, but does that really matter? It's not a big enough difference to mean anything to anyone.